So we look at our BJT circuit configurations, which we have just highlighted in the previous lecture. So the first configuration is called Commandbased configuration. It's called Commandbased configuration because the base is common to both the input and the output circuits of the configuration, right? And also the base in that case, it means it's usually the one which is closest to ground, or the lowest potential relative to others in terms of closeness to the ground. And we remember that the current, when we talk about current in any transistor circuit configuration, we're referring the current with respect to the direction of the holes, which is the positive. Remember, conventional current moves in the direction opposite that of electron. That means it moves in the direction of the holes. So we bias such a circuit so that we establish the current in the direction which is required for each branch. So for a PNP configuration, you see that the arrow is pointing into the transistor, right? It's pointing into the transistor, showing that our holes are moving in that direction because it's a P, right? N and P, right? So our configuration for NPN, electrons are moving in that direction, so our current is moving in the opposite direction. So this arrow will show you the direction of the conventional current. And yes, you can see our base is the one which is, in this case, it is actually the ground, or sometimes it's closer to the ground. Again, it's common to the output circuit, which is the collector circuit, and the input circuit, which is the emitter circuit. The common-based configuration, we look at the characteristics, that is the input or driving point characteristics, and the output or collector characteristics. So our driving point characteristics are referred to the emitter in this case, and our output characteristics are referred to the collector in this case. And we have three operational regions, like we said, the active region, in which the base emitter junction So this is what I was talking about, active, saturation, and cutoff regions. Then in the common-based configuration, we are saying IC is approximately equal to IE. That means the input current is approximately equal to the output current, right? Then when the transistor is switched on, the base emitter voltage becomes 0.7, so it becomes fixed at that point. So you realize that in our calculations, once we establish a forward bias on the base emitter circuit, automatically we know that the voltage across these 2 points is 0.7. So that is one voltage which you don't wait for someone to tell you. you know that this voltage, as soon as you know that this is forward biased, that voltage is 0.7. What changes is the voltage across the collector and the emitter, right? So in the DC mode of application, we are saying the current gain, which is the output current over the input current, is given by alpha, right? In other words, we are saying the small current gain that we get when we are driving our transistor in the active region is beta. That's why I was saying IE and IC, they are almost equal on that graph, right? So if we ignore this current, right, then we can approximately say that alpha is equal to IC over IE. So that will be the small diffusion current that will always exist. So alpha is our common gain current, our common base current gain factor, right? Then when you want to bias this, all what we are saying is that make sure you forward bias the base emitter junction and reverse bias the base collector junction for you to operate in the active region. So if it is PNP, what you are saying is that the emitter should be the higher potential than the base for forward biasing this, and the base should be the higher voltage than the collector for reverse bias of this circuit. If it is NPN, it means the emitter, which is the N side, should be the lower potential than the base. The collector should be the higher potential than the base for reverse bias, and here for forward bias. So when you are looking at this, we are saying our input side is our emitter side. So in other words, we are saying with this small voltage, we can give a bigger output, that is amplification. And as you can see, we have a low input impedance there and a higher output impedance on that kind of circuit. Then we go on to the common emitter configuration. Again, the emitter is common to both the input and the output. In this case, our input is the base and our output is the collector. Again, it is connected to the ground. That closest to the ground, and this is a higher current gain and voltage gain, right? So again, we know required bias for PNP and NPN for active region. But what we are saying now is that a small IB with a big gain here will give a larger IC. So in this case, you realize that IE is what IC plus IB, right? So the current that is injected into the collector, comes out of the collector here, is the sum of what goes there and what goes in that circuit, right? So again, as you can see, if you have a greater VCE, then your current quickly increases, right, as you increase your base emitter voltage, right? So IB is in microamps, and then IC will be in milliamps. So when VB is greater than 0.7, that is our barrier potential for the silicon there, then we have forward biased our transistor, and then it can give you a large gain. So as you can see, with an IB of 60, you can 60 micro can get up to 6 milliamps. That means the gain here will be about what? About 100. If you took a look at 6 milli over 60 micro. In other words, the current gain in the common emitter configuration is very large. So you read that this is also commonly used in our transistor as an amplifier circuit. The bias is still the same. The base emitter junction should be forward biased for active region. This is where your current gain beta will be significant. Saturation, there's no control of the current by beta in here. Nothing is flowing. It's like before. So the amplification factor beta will be equal to IC over IB, right? So for AC condition, AC beta has been defined as the change in collector current compared to the change in base current. So in data sheet, you might find the HFE also being referred to as our beta. In our case, we are to the DC circuit. So in other words, we are saying you should be able to calculate your beta if you are given the currents, right? So from our common emitter connector, find beta AC and beta DC. In our case, we don't care about this AC or DC because we know we are dealing with DC. With an operating point at IB is equal to 12 microamps and VC is equal to 0.7.5. So beta, that's IC over IB. Then at that operating point, this is the change in IC, this is the change in IB. This is to this graph. So we are taking our measurement from that graph. But in our case, we'll mostly just give you the values, then you do the calculations. But we are saying operating point, if they say the operating point VC is about 7.5, right? Then looking at a value of 7.5, right? Then we also look at the given values of beta, right? So this will be your Q point there, right? Then you find your values like that. So if you want to find the relationship between alpha and beta, you use our knowledge that IE is equal to IC plus IB, and also IC is equal to beta IB, right? Then it means IE is equal to beta plus 1 IB. Do your simple maths. For alpha is equal to IE over IC over IE. And then IE is equal to IC over alpha, right? Then IB is equal to IC over beta. So if you substitute for IE and IB into this equation, you find out that alpha is equal to beta over beta plus 1, and beta is equal to 1 alpha 1 minus alpha. So you should be able to know how you deduce the relationship between the two. Then common collector, it's almost is a common emitter in terms of the parameters. So it is called common collector since both signals, source and load, share the collector terminal. Output is obtained at emitter terminal. So in this case, our input will be in the beta circuit, in the base circuit, sorry, right? Then the common collector configuration, it is provided with the load resistor connected from the emitter to the ground. It is used primarily for impedance measurement purposes since it is high input impedance and low output impedance, right? So you see that the common base, it's low input impedance and high output impedance. Common collector, high input impedance and low output impedance. So that is the configuration and how you bias that. So the common collector, the output current plotted is given. So as you can see, this is almost the common emitter, right? So we also look at the limitation that we have on using our transistors. Look at the power dissipation, that means you have to limit it to a maximum, right? So in the output, the collector, maximum collector emitter voltage so that we don't reach breakdown. Then also maximum collector current, this will also help us in order to control our maximum power dissipation, right? Remember, we need to operate in the active region if we want to use a transistor amplifier. So if you get this limitation, then you know that this will be your operating region outside which you cannot use the transistor safely. That means it will blow out, right? So that's an example. Maximum collector power dissipation, PD. That's IC max times VCE max. That's 360 milliwatt. At any point on the characteristic product, the product of VCE and the IC should always be less than or equal to 360, right? So this will be your maximum power dissipation, which means what we have here will be our operating region for the